Hey everyone, welcome to this explainer from Forge College. I am absolutely thrilled you're tuning in today. Okay, let's just jump right in, shall we? Today, we are going to explore exactly how to handle things when our previously perfect Hardhat tests suddenly, inexplicably, decide to fail. Now, if you've been following along with our Ethereum dev stacks and frameworks track, specifically in our Hardhat fundamentals module, you'll remember that in our previous lesson, we completely mastered interacting with the blockchain in our tests. We sent transactions, we read state, we built solid assertions. It felt great. But as literally any developer will tell you, that perfectly passing logic doesn't last forever. So today, we're going to learn the art of the fix. In our last lesson, everything was peaceful, right? We had those beautiful, passing green terminal outputs. But today? Well, today we are walking into what feels like a full-on developer's crime scene. I'm talking about a completely broken continuous integration pipeline, a massive, terrifying wall of messy red terminal text, and that sudden urge to just question all your life choices right before you try to merge your code. We have all been there, and honestly, it can be incredibly frustrating if you don't have a solid game plan. So, I want you to ask yourself a question right now. What is your very first move when a test suddenly fails? For a lot of us, the natural human instinct is to panic. You might start sweating a bit, randomly tweaking variables, or blindly rewriting lines of code, basically just crossing your fingers and hoping the compiler decides to magically forgive you. But instead of panicking or doing that dreaded guess and check dance, which, by the way, is especially dangerous and expensive in Web3, we need to put on our detective hats and approach this whole debugging process systematically. Step 1. The scene of the crime. Every good investigation starts by securing the scene and confirming that a crime actually took place. Your very first step here is incredibly simple, but it is so easily forgotten. You must run npx hardhat test locally, right on your own machine. Why is this absolutely crucial? Well, because we have to make sure the failure isn't just some weird transient glitch in the cloud, a temporary network timeout, or your CI provider just acting up. We need to see a reproducible error right in our own terminal. Because simply put, if you can't reproduce the bug locally, you can't fix it. Once you've actually got that error right in front of you, you've got to ask the ultimate debugging question. Is the contract lying, or is the test confused? Think about it. You have two totally separate code bases trying to agree with one another. Did your smart contract misbehave and calculate something wrong? Or did the contract do its job perfectly and you simply wrote a flawed expectation in your test? Figuring this out is your primary mission right now. Step 2. Securing the perimeter. To answer that ultimate question, we really can't afford to be distracted by dozens of other passing tests. We need absolute focus. Imagine trying to listen to one specific conversation in a stadium full of screaming fans. That's exactly what running a full test suite is like when you're hunting for just one bug. So by appending .only to your Mocha it block in your code, or by running npx hardhat test with the grep flag, say, for example, grep increments twice, you are effectively putting up police tape around that single failing test. This drastically cuts down the console noise, saves your computing power, and speeds up your feedback loops so you can iterate super fast. This essentially gives us our core detective methodology. It's a really simple 4-step process. First, we reproduce the error locally. Second, we isolate it to cut out the noise. Next, we inspect the internal state of the smart contract. And finally, we snapshot our testing environment. By treating debugging as a structured procedural checklist rather than a wild guessing game, you are going to save yourself hours of pure frustration. Step 3. Gathering your evidence. Okay, with the perimeter totally secured and the test isolated, it's time to gather some concrete, undeniable evidence from the code's execution. Believe it or not, even in the highly complex world of Web3, the humble console.log is still one of your absolute best friends. We can inject console.log statements directly into our JavaScript test files to peek at those intermediate values being returned by the contract right before the assertion failure even happens. But just remember one absolutely vital detail. You must await the promise to ensure your logs appear in the correct sequential order in the terminal. If you forget to await, you're just going to print out a pending promise object, which is, let's be honest, about as helpful as a magnifying glass in the dark. Now, what if the bug only happens sometimes? If test order or previous blockchain transactions are causing interference, we bring out the heavy hitters: EVM snapshot and EVM revert. Think of these commands as your personal developer time machine. They guarantee that we are wiping the slate clean and inspecting the exact same chain state every single time we run the test. This is actually a really crucial technique we rely on frequently in the more advanced Forge College courses to ensure true determinism in our testing environments. Step 4.
identifying the culprit.
All right, we have our evidence. Now let's examine the output. In our sandbox project's counter.sol contract, our code simply increments a count variable twice. But surprisingly, our chai assertion fails and it spits out this error, assertion error, expected 2 to equal 3. So the actual value returned by the contract was 2, but our test was stubbornly looking for a 3. The mismatch is clear, but where exactly is it happening? To find the exact location, we have to learn how to read a stack trace without getting totally overwhelmed. I know, stack traces can look incredibly intimidating because Node and Hardhat just dump dozens of lines of internal framework files onto your screen. The secret? Just ignore all the framework internals. Seriously, just scan for the very top frame that contains your own test file path. By doing this, we see the error points exactly to line 14 in test/countertest.js. Boom, that is our smoking gun. We bypassed all the noise and zoomed right in on the exact failing assertion. So, this brings us to a massively important rule of thumb. Prefer changing your tests only when the test expectation is objectively wrong, rather than blindly changing your contract behavior without clear evidence. Let's do the math on our sandbox project. The counter starts at 0, we call increment twice, each call adds 1, therefore 0 plus 1 plus 1. The contract returning 2 is completely mathematically correct. The contract's behavior is actually perfect. It is our test expectation of 3 that is completely flawed and confused. Armed with this deduction, we apply the minimal fix. We do not rewrite the entire smart contract logic, which honestly is a trap so many eager beginners fall into. We simply update our chai test assertion on line 14 from .2.equal3 to .2.equal2. Then we run our perfectly isolated test one more time, and we get to sit back, relax, and watch it pass with flying colors. Step 5, closing the case. As any good detective will tell you, no investigation is ever truly complete without filing the paperwork. Documentation is key, folks. For your upcoming capstone project, and honestly on any professional dev team, you'll need to compile a concise 6 to 10 line debug report. This report acts as a historical record. It needs to detail the original failing assertion, the exact CLI commands you used to isolate it, the root cause, which was our off by 1 test expectation, the single line patch you applied, and finally, the verified passing output. This proves not just that you fixed it, but that you understood exactly why it was broken in the very first place. By mastering this highly structured, evidence-based approach, you aren't just fixing a broken test today, you are laying down the foundation for scalable engineering. So ask yourself, are your debugging skills ready for a fully automated CI pipeline? Because once you know how to reliably isolate, diagnose, and document these failures, you are perfectly prepared for our next step, designing maintainable test directories and robust continuous integration hooks that prevent these bugs from ever reaching production. And with that, our investigation comes to a highly successful close. To dive even deeper into testing frameworks and really level up your engineering workflow, be sure to check out our other explainer content. We highly encourage you to visit forge.college to master Ethereum dev stacks, participate in our amazing learning programs, and explore a whole world of other exciting Web3 topics. But before we go today, I want to leave you with this one thought. If your test suite is supposedly responsible for guarding your smart contracts, who is responsible for guarding your tests? Think about that, keep your scope isolated, and happy coding.